Good morning. My name is Anirudha Jadhav. I work at Bloomberg LP. The talk over here I'm presenting today is Never Stop Exploring and Pushing the Limits of Solar. It's kind of a vague title, but what I'm leading towards over here is we run numerous solar applications, and every single person comes to us with a very different use case, which is, first it begs the question, does it really deserve to be in solar? Then the more you think about it, it perfectly fits, but every single use case that comes to us is kind of, in a way, trying to do something which everybody else is probably not thought about. So every single use case that comes to us is very different, and I'm going to talk about one use case today and explain to you the tests, benchmarks, and what came out of that. So who am I first? I am a NYU graduate. I worked in the credit derivatives world at Bloomberg for some years. Soon after that, I loved search. I was working a lot with Lucene earlier in college and went back again to working with Bloomberg Vault. Bloomberg Vault is an enterprise compliance product, and we are arguably hosting one of the world's largest Lucene deployments right now. After that project completed, after a few years, we moved ahead and built a search as a service platform. Everybody's doing that nowadays, but most fun I've had over there is considering how diverse the company is. We get use cases from every aspect of life, and I'll just touch on a few of them later. And currently I work in big search, distributed databases, and anything around scale. Bloomberg is primarily a data company. We are an information company. We have many different verticals and aspects of it that people don't know. Most people hear about things which are available to them in the media. You can just go walk to our booth or go to the website to figure out more information on the company itself. I'll not take much time here. For this particular talk, we'll talk more and just touch on search at Bloomberg, what are the different aspects of it, and how this kind of a project came into being. Talk more about a little bit background to understand the base concepts which I'm going to be covering, factors that affect indexing, share our tests and benchmarks, and run through some numbers over here, and propose a new design for an NRT indexer, which will do way better than what we have right now. So search at Bloomberg. We have a lot of different teams across the company which use search. Around more than 100, 200 people use us. I'm just point out a few things over here. News search is primarily our major driver. We have the world's largest aggregation of news wires coming in from across the world. They're coming at really a high, massive rate. So latency of ingest is a big factor over there. Federated search. We have so much data in various different search use cases. How do you search across? And when you search across, the major problem is not just getting there and getting the data back up, but it's also about re-ranking and ranking between those things correctly. Archival search is Bloomberg Vault. We are pushing at more than 185 billion plus data sets, and we search over them real time and live. There's geospatial stuff going on, a lot of cool work done in geospatial. Analytics and statistics. Yesterday, one of my colleagues presented on a component which we open sourced recently to the community that basically helps you to do analytics on top of Solr. So to my actual presentation, we were tasked with an idea, which is basically, what do you do, and is it even possible to build a market-facing application on Solr? What that means is you have high-frequency updates coming in from market streams. Is Solr an engine which can serve high-frequency ingest? And this is, initially when you hear about it, you kind of don't want to do it. It's not meant for it. But the more you think about the usage pattern, how data is getting used, how people are going to use after getting ingested, it makes complete sense. So we are trying to see at what point can we break it, and can we achieve a middle ground where we can sustain performance. So let's do a little bit and go into the background, understand the indexing workflow in Solr, and then walk towards some basics and the actual solution we proposed. So just to recap, indexing in Solr cloud is like you have multiple replicas with one single leader. A single client sends a document to a replica, it forwards it to a leader, updates the transaction log, and this is a pure CPU system over here. The difference over here is the transaction logs are updated as a CPU system, and you have synchronous updates, synchronous operation going on, but the data which is available for search is still not available as soon as this is done, because the updating a transaction log does not mean a searcher is available so that you can serve search results over it. So that's a key point of note. Going ahead, after data is in the transaction log, there's a huge analyzation chain. It starts with tokenization, downcasting, segmenting, stemming, stop word, synonym, and all these can use in various orders. You can have one or more of them. What this basically tells us is it's very complex, and whatever solution we provide, it's not going to be a one-stop solution for everybody who tries to use us. So search is a very generalized problem with varying complexity levels. So the factors affecting indexing are data type and data distribution. I'll talk a bit more about each of these factors. And all these factors together play an important part in designing a search index. But a search index is really, you have to focus on designing the search index if you're building a search application. Query speeds, all the performance you are gaining is very highly dependent on how you design the search index, how large do you want it to be on the class of machines you have, and various factors that play into role. So going ahead, I'll just go through each factor at a time. So data and data distribution of tokens. What is important is once you have textual data, primarily Solr is used for textual data sets. You can classify textual data sets into two aspects, machine-generated data and human-generated. The difference over here is the distribution of tokens. In machine-generated data, you have few tokens. What this really ties out into designing an index is you have 100 million documents of machine-generated data. When you see the index size increasing and all the data structures, how they increase on disk, you will see a spike initially and then literally a plateau. There'll be like a gradual increase. If you have human-generated data, it is very different. So based on that, you can provision for hardware, and you can see for this class of hardware, if my SLAs are supposed to be 2-second query performance, 2-second ingest per performance, 50 millisecond query performance, this is the size of an index that can serve with these many cores and this much memory on my machine. So what is important over here is how do all these things affect search engine design? Search index, distribution of tokens, whatever query speeds you want indexing, the core thing I'm getting at is design your search index correctly, considering all the factors in your application, and once you have that done, everything will fall in place. Going ahead, once we have the search index and data, let's go to the server. At the server-side design, typically you have some numbers. I prefer at least have 2 or 3 Solr cores per CPU. Solr is purely a memory-bound process. You give it as much memory as possible and it will be happy with you. If you don't have it, enough swap space or SSDs, and you can do well. Disk space, you have to be worried, because Solr always does this optimization cycles and merge cycles at which it doubles its index size. So you have to make sure that you have enough headroom for these cycles on your servers. Memory, so with respect to memory, for my applications, I try to make sure that I use as little JVM memory as possible and as little heap as possible. Caching is a very intensive operation which uses a lot of memory, but for anything high frequency, caching is not useful because you are invalidating your caches periodically. So at that point, you really have to consider, are caches worth it, and do we want to spend that much effort and time in warming up every single time? Doc values are really great. Doc values are on-disk data structures. There are these inward indices which are kind of like columnar stores for Solr on disk. A lot of new stuff is coming up with updating doc values without updating the entire document, similar to external file fields which we are used to right now. So all those features and the value that doc value provides, that it is not in the JVM heap. And use mmap memory, go away from the heap as far as possible, and your server should be good. There are other considerations that play into part at the networking aspect. So you have to decide how you want to span your clusters and where are your actual data centers. If you have a single data center, one single Solr cloud is like a straight off answer. If you have dual data centers, do you run active-active, active-passive? Do you run one single Solr cloud across 2 clusters? All these considerations play into account, and you have to see what's the latencies between them. And often people miss out, where are my zookeepers? Where should they live? What are the considerations for a zookeeper quorum design? So these are all the factors we were looking at while optimizing the high-frequency ingest use case. But as it turns out, all this design consideration are also useful for debugging and troubleshooting when you have an issue. Like, go through this checklist first. If everything over here maps up, then maybe look inside code and figure out what's the other things you can do. Concurrent connections to a server. There are some limits on Jetty. Solr does this management pretty well. There are good defaults selected, but you should keep an eye over there. Network latencies and QoS guarantees. If you run in your own data centers, there are separate networking teams which do all this work for you. But if you're running in Amazon or any other cloud infrastructure, it might help to just take a periodic look into what the network QoS guarantees are and how they affect your performance, because these clustered applications have a lot of talkback between nodes. Client-side factors. So managing reusing connections. If you are using Java, most of the libraries do this job pretty well. We were using Java, we use Python, C, C++, various languages to send data, and managing and reusing network connections was a major issue in that world. That's why I have it over here mostly. Now comes to how are you sending data to the server? This is very important, and this has a huge role to play with performance. Everybody would accept Java bin is the compressed format. Java bin is really a Solr serialization format. It's not a Java serialization format, just called Java bin, just to be clear. The Java bin serialization format is good if you have documents which are smaller and which have less metadata in them. As you grow more and more metadata, more field types appear. What really happens is most of your transport is taking up in encoding those field types, encoding those object serialization techniques even when they're flowing over the wire. So the best which I have found is based on what type of data you're sending. CSV is the most optimal technique because you have the headers only sent once and you're only transporting data after that. Other than that, in descending order are JSON, XML. These formats are really expensive. I would definitely recommend not using them. JSON serves some value when you're operating with external systems. And how many simultaneous threads are you planning to use when you are shoving data into a Solr cloud system? You don't want to bottleneck or choke the remote server also. So this is one consideration you have to see. So we played around with numbers all across these factors. And after going through all these factors, varying these things and running some experiments, I want to share with you this key insight we found out. So I tried to coin these three terms. The important thing to understand over here is the collector. A collector is a buffer that collects Solr document updates. So you have an indexing process, a client indexing process, which is getting streaming data or which is getting high frequency updates to it. What the client process does is it starts collecting or buffering or batching things. Now how you batch these things, we came up and coined these terms: time triggers, document size triggers, and document number triggers. They're really simple concepts. The collector is only active for 5 milliseconds. Whatever it could collect in 5 milliseconds, it will batch in and send out. And we varied these numbers around and saw how the performance varied. So we have time triggers, which work on time-based factors to collect. Document size triggers, which basically depend on how many number of documents is the max threshold, and you cut off after that before you fire off. And the document size triggers, which is basically a buffer size. These three collectors, we use them together because if you have a time collector and you have spiky data, you will basically overflow your buffer sometimes, and updates might fail because of some other factors. So you want some guard parameters. So the three parameters we have take part in a priority system, where the first priority collector is what we always make sure should fire all, and the other are kind of guard parameters to that. So the kind of tests we did are as follows. The system of benchmarking we followed is a client application sends data to a 4-way replicated Solr cloud. It's a 5-node Zookeeper ensemble. Tests are done with a similar data set right now. So the numbers I'm sharing over here for this test, the benchmarking setup is only for that. We tried various other tests for this. We synthesize a high throughput ingest stream, which serves as our input, and soft commits are set at 1 second. With this in mind, let's look at our first test. So our first test is 5 millisecond window. So if you consider the 5 millisecond window, the documents which we collect over here are a little bit lower in value. So if you want to consider this use case, it's the actual Solr NRT use case, where you're sending a single document. As you collect more and more document and batch them up, the performance increases, but it hits a sweet spot. After that, it keeps on decreasing out. So this is a heuristic, but we want to guard our heuristic with several thresholds. So the second priority metric which we use in our tests is document limit test. So document limit test is just a number trigger, second guard, and the performance which we saw over here is we were conservative. We didn't have higher numbers in here. The documents which we used in this particular tests were small documents with 10 fields. So we could fit a lot of documents in a single batch request. And this also observes a similar pattern. As soon as you keep on increasing, you get a sweet spot, then performance slowly goes down. But we don't want every metric to be at its peak. Others should be guard, and the top metric, so we ran some benchmarks to figure out which one works the best for our environment. Next is byte limit text. This is a third level threshold as a guard metric which we have to our heuristic. And over here we see as we keep on increasing, the size of our buffer, the rate of update documents per second just keeps on increasing. Eventually it goes up and falls down. So the key metric, I'll just take questions at the end, sorry. So the key metric I'm trying to convey over here is, on an average, with not just machine generated data set, but various data sets, we were able to achieve 5 to 7x increase in performance. This was what we could sustain with our buffer parameters, that we are not overshooting and we're not always at max performance. At max performance, these were easily over 10x. The optimization parameters needed constant changing. So this is an important point. When you have a Solr cluster setup which is empty, you will get peak performance. It's like really blazing fast at that point. As the index size grows, it slows down, and we used to have to tune performance. So 15 milliseconds would be a good number, but slowly it was like 12 milliseconds, 10 milliseconds, 5 milliseconds. And again, based on the kind of machines you're running, this will vary for you. The tuning variables, because of the fact they're constantly adjusted, it became a difficult thing for us to use. So we use this right now in production, it works fine, but we benchmark and test for a higher level peak and set it at a very low level where it performs well. Now, in the remaining part of the presentation, what I would do is, how do you get towards a design for a better near real-time indexer, which wouldn't need all these tuning knobs, which wouldn't need constant human intervention to like change this, change that, benchmark this. So what I'm getting at is, have you ever steered a ship or been in a kayak or something? Whenever you are changing direction, you have to take into account what's the current, where your rudder is, and everything is relative. Coffee machines use similar principles. If you have an espresso machines, the Nest thermostats use a similar principle. A lot of things in your daily life use similar principles. And what I'm going at is control systems theory, where you have a PID controller. What the PID controller effectively does is it takes into account the current and the present error, series of past errors, and sees what is the rate of error right now, or rate of change right now, and combining all these three factors, what should be my future output. So what I'm getting over here is kind of a design for a client indexer. So just to convey all the points first. This entire red box is a client indexing process. Solr Cloud is right here. We have a sampling thread which keeps on constantly evaluating docs per second, which it is observing from a Solr Cloud update loop. The PID controller implementation goes in between, and these are the indexing threads. So our control variable is time. There are other two variables. It's very complex if you have three changing variables in a PID controller. At that point, it's better to move to a different algorithm. But since we are basing everything on a priority-based mechanism, I have the control variable to be the primary time variable in my metric, and other two still act as thresholds. Once we have the PID controller implementation in place, what we observed over here was the same block diagram with and without a PID controller implementation. We were able to sustain speeds to an extent. So when you start a Solr Cloud setup, it is blazing fast because everything is empty at that point. We get peak speeds. As the index keeps on growing more and more, we have set index limits which we cut off. But as the index keeps on going, the performance keeps on reducing down. So at that point, what we want to do is compare this with an actual similar setup without the PID implementation. And what we observed that the constant tuning on parameters was not required as much. So these are the tests we've done. We want to add more things into the system, and we want to try to see where we can take this in the future. So what we are going towards right now is perfecting the PID implementation in a standard form which we can use together. adding it to the YCSB framework. The YCSB framework is a cloud benchmarking framework. It basically has various data sets. The distribution of data varies, so you can test a database with different data sets and see what's the performance like. The key thing what I also want to do, and what we were like, we're not getting at it, but as a side effect, you can actually use the PID indexer or the same framework even without the PID indexer and manually tuning the parameters to size a machine. For a particular data set, which class of Amazon machine do you want? Do you want the large one, big one? How much memory or RAM do you want? It really depends on your data set. If you run these tests and keep on varying these parameters and understanding all the factors which we talked about previously, all these take part in designing the correct size of a search index. Other parameters which we want to add in the PID indexer were, okay, my index is growing over a period of time. I don't have a set boundary where I keep on purging. Because I don't have that, if it keeps on growing, the performance will constantly keep on getting degraded. So we want to add server-side parameters inside the indexer where it will be reach a threshold, cut off to a newer shard. Reach a threshold, cut off to a newer shard. And we did testing with 5 shards and constantly doing this performance increase, and we saw linear performance gain up till 5. There will definitely be a sweet spot way up there, but we didn't go beyond that limit now. So this is most of our work into high-frequency ingestion. We saw great performance boost with Solr near real-time ingestion over here. And if you have any questions, I'll take them now. Thank you so much, guys.
How are you ingesting those documents? Like what technology? Are you just using Solr J to do that?
So for our ingestion, we have client libraries written. And we are using kind of similar things Solr J does, but we come from a C++ framework, so we are using curl. That's why the more importance on stressing into connection reuse and connection management. Most of the Java libraries do that on your own. I couldn't hear you, sorry.
Regarding the byte limit test, did you see any degradation after a period?
So regarding the byte limit test, yes, we did see a degradation. The reason I'm not showing that over here is I want to make a point really clear that 3 of them should never be used together. The other 2 are really guards. And the guards are basically guarding you against your network packet buffers. Sorry, come again? Data source. So data source is coming from market data. We're getting market streams.
So it's a file format?
These are actual market streams coming in.
Okay, the second thing, actually, we observed some of the performance issues, not from indexing, but because we have a lot of things, so we observed when we index data, and every sometime when the replication starts, the indexing completely stops for a couple minutes.
It happens sometimes. If you choke the leader.
No, actually, we don't use the Solr cloud. We just have one master slave, one master, 2 slaves.
Okay, I'll just take it offline.
Okay.
Thank you. Anything else?
Did you also get to test how it was impacting the query time?
So the question was testing query time performance. The query time performance we did test, but we were not trying to optimize query time because most of the query time performance tests we are doing were under 50 to 100 milliseconds. So around that, we never really focused on that aspect of it. But if you are looking forward to query time performance, what you are really doing is scaling out wide. So as far as you have your indices small and enough RAM, you should be fine. Unless you're doing compute with analytics component or some other compute heavy component in Solr, spatial or something else. At that time, you need to be worried about optimizing your queries per se. But faceting, pure search features, you're good. Scale out wide and you should be okay. Any other question? Yeah.
You were talking about the importance of the input format to performance. Have you tried any the binary message formats like protobuf or Avro?
So Solr has this named list, or I forget what it's called inside, and to get everything in correctly is a lot of work. But we did benchmark with Solr bin. If you compare Solr bin and like not compare, just understand what Solr bin is, what protobuf or Avro, everything, all these guys are, they're kind of not very far away. Solr bin is optimized nicely. It works. It's sort of just a Solr serialization format put into together. But the way you see performance in that is if you have the documents which have a lot of fields, the serialization of those fields take up too much space in the transport. So it really depends between Solr bin and CSV on your data sets, which one you want to choose.
As far as data formats, where you were explaining that CSV worked out the best for you, let's say, could you explain a bit what's the difference between that or, let's say, using JSON or XML? What was the deciding?
It's just the compact structure. You don't have, it's just a size of data sending basically. And CSV does support multi-valued and everything, it's all there. Most people just stay away from it, but I would say just take a look at it, it's good, it works.
Regarding the number of threads that the client uses, do you have some rule of thumb over there?
So no, I don't have a rule of thumb as such. We have, so the similar benchmarks, I also had benchmarks with number of threads while keeping other things variable. It's built too complex to explain in a small presentation, but number of threads do affect a lot. You have to test. There is a pattern which emerges out, but the pattern is very different per application and the size of data per document. So that's why I chose to just ignore it from this presentation right now, but that is a major consideration.
Also, actually, the server, the Solr server, the CPU memory actually there as well.
Yeah.
For us, we have the 16 thread, and we run the CPU.
Okay. Any other questions, guys?
You're doing 25,000 talks per second. What was the general size of those documents?
I would say around 10 fields, and each field was around 15 characters max. It's not like tiny, it's decent. But there's also a very important things to be said about the class of hardware we run on, so I wouldn't take those numbers and go with that.
Did you mention your commit strategy?
1 second soft commits with 15 seconds hard commits.
What's your main bottleneck? Is it the query time, ingestion, or?
So query time is not a bottleneck per se because you can scale it out wide and it works. But you have to see at that point how wide are you scaling and can the replication stand up. This was particularly focusing on ingestion. So for ingestion, the main bottleneck which had is how to get data to Solr faster and in a more efficient format. So most simple approach is send one document at a time. We tried to go beyond that and see what we could observe. Any questions, guys? Sure.
What sort of impact did the 1 second comment had on the use of memory? So with each comment, there would have been a new search purpose if there was a query or a.
So this is a soft commit, so everything is in memory.
But even with a soft comment, there is a.
There's a thing, but it's all in memory. As long as you're not on disk, it's not as much. The numbers and tests we did with 1 second soft commit is like really something, like one second is a really low number. Not a lot of applications use it. I don't recommend a lot of people to use it, but we tried to see how much lower could we go, and with an extent like, I hoped 1 second will not work, but let's just try it. But it worked so well, like, let it be.
And what was the size of the index on the disk?
Size on the index, we started from scratch. As I mentioned earlier, when you start from scratch, it really shoots up. So we waited until the size of index got considerable. I cannot disclose like most of the index size numbers, but for this particular test, we started off from scratch, and all these test numbers were gathered when the index size was at least 5 to 10 gigs in between there. And from there on, we kept on sustaining. But as the size on disk for the index grows, performance does degrade. So at that time, you want the client strategies to shard off. And with sharding, we saw linear growth. But that will again degrade after maybe 10 shards. With around 5 shards, it was like really nice. So thank you guys. We are out of time. We can just catch up later. Thank you.